How do PID controllers reject system disturbances? Imagine you're steering a boat across a choppy lake. Every time a wave hits, you need to adjust quickly to stay on course. That's similar to how a PID controller works to keep systems steady when disturbances occur. PID stands for proportional integral derivative. These controllers are used in electrical engineering to regulate systems by changing control signals based on the difference between what you want and what you actually get. When a disturbance hits, like a sudden load change or environmental noise, the PID controller steps in to fix the problem. The proportional part reacts instantly to the current error, which is the difference between the setpoint and the actual output. If the error suddenly increases because of a disturbance, the proportional term immediately increases the control effort to counteract it. This quick response helps reduce the error fast. The integral part looks at the history of errors, adding up past mistakes over time. If a disturbance causes a steady error, like a motor running slower because of a heavier load, the integral term gradually increases the control signal until the error is eliminated. It helps the system settle at the right point without a constant offset. The derivative part predicts how the error will change in the future, based on its current rate of change. If the system starts to oscillate or overshoot after a disturbance, the derivative term acts like a brake, damping those oscillations and helping the system stabilize faster. Together, these three parts work to reject disturbances by constantly adjusting the control input. When a disturbance occurs, the proportional term responds immediately, the integral term corrects any long-term offset, and the derivative term prevents overshoot and oscillations. This combined action means the system can handle both sudden shocks and slow changes effectively. In electrical systems like motor speed control or power regulation, disturbances often come from load changes or supply fluctuations. For example, if a motor suddenly faces a heavier load, the speed drops. The PID controller detects this error and increases the voltage supplied to the motor. As a result, the motor speeds back up to the desired level. Getting the right response depends on tuning the PID gains, which are the proportional, integral, and derivative constants. Proper tuning ensures the system reacts quickly without excessive oscillation or sluggishness. Engineers often use methods like the Ziegler-Nichols tuning technique or software tools to find the best gain values for each specific system. While standard PID controllers are very effective, they have limits. They might struggle with very fast or complex disturbances or systems that behave in nonlinear ways. In such cases, advanced techniques like feed-forward control or active disturbance rejection control can be used. Feed-forward control measures disturbances directly and adjusts the control signal before the disturbance affects the system. Active disturbance rejection controllers estimate disturbances in real time and cancel them, providing even better performance. For most electrical engineering applications, especially those involving linear systems and common disturbances, a well-tuned PID controller offers a simple, reliable way to keep systems stable and accurate despite external shocks. It's like having a smart autopilot that constantly adjusts to keep your system on course, no matter what comes its way.